Hi, folks. Welcome to the Graphics Programming Virtual Meetup. So today's topic is this paper, a survey on bounding volume hierarchies for ray tracing. Our meetup follows the Berlin Code of Conduct. We have a Discord server, and we have a Twitter account to announce meetings, and we also have a YouTube channel for past recordings. As I said before, the topic today's this paper, a survey on bounding volume hierarchies for ray tracing. It is a survey, so high-level overviews on different algorithms and techniques that we can use to implement bounding volume hierarchies. It does not go into depth into too many stuff. So if you need to implement a particular technique, then this paper have linked to other papers where you can go. It is a great overview on what is there and what you can do. Also, because the information density of this paper is very high, I unfortunately need to leave a lot of stuff. So if you really want to have a better picture, then you need to read this paper instead of just watching this talk. So the agenda today is a several part. First, we will go through the preliminaries of what a BVH is and some other background. And then we will go through the cost function of BVH, how to construct them, what is some extensions that we can make into the BVH, how to traverse the BVH, and also some other BVH applications, the best practices to implement BVH, and some other open problems, which is roughly how the paper gets structured. So first we will talk about preliminaries. What we want to find with BVH is nearest intersection, any intersections and all intersections of array within C. Nearest intersection is what we usually want to find. Any intersections means whether we intersect with ray at all, or whether a ray intersect with something at all. The terminology here is different from the RTX any heat shader, which is actually all intersections in the paper's terminology. So all intersections means we need to find all of the intersections instead of just, and that's also how the any heat shader get invoked. It is when we just invoke it on all the intersections. And naively, we can do ray object intersections by per ray per object, but that can get pretty expensive. So we can reduce the ray object intersection test by using some kind of acceleration data structure. And this changes the problem from O of n object to O of log n, where n is the object. And bounding volume hierarchy is the most commonly used acceleration data structures nowadays. The other one commonly used is KD tree, but BVH is more prevalent. And this paper is exclusively about BVH. So BVH is the rooted tree with arbitrary branch factor k. Traditionally, it is binary. It is a binary tree, but we can see later that in cases we will have the branch factor that is not true. Also, if you have done shader toy before, then probably you have constructed the BVH with arbitrary branch factors. And An interior node refers to its children and the bounding geometry, and the leaf node contains the primitives. So the bounding geometry is used to get a rough idea of whether array intersect with interior, with the children of the interior node or not. There are several different kind of bounding geometries. AABB, which is most of us most familiar with, also oriented bounding boxes and bounding spheres. And I have seen blog posts on other interesting bounding geometries. There are several advantages of BVH. First, it has very predictable memory footprint. For example, for a binary tree, binary tree BVH, you cannot have more than 2 n node if you have n objects. So you can know an upper bound of the BVH if the upper bound of memory consumption of the BVH if you know how many objects you have. BVH is robust and has efficient querying, and also it has scalable construction, which means there are tons of algorithms on how to construct BVH. Some of them are higher quality and some of them are lower quality. But lower quality ones usually construct faster. So for real-time applications, we probably will use lower quality BVH. And for offline rendering, we will use higher quality BVH. And because the total render time is the BVH construction plus retracing. So we can't take too much time on BVH construction if our BVH changes a lot, and then our retracing time is really short. So let's also come to the next point, which is dynamic geometry, where it is considerably harder to implement in other acceleration data structures such as kitty trees. Now let's talk about cost functions. So cost function is an estimation of the expected number of operations needed for finding the nearest intersection. So cost function of a BVH with root n can be described with this recurrence relationship. Can you see my mouse?
Yeah, we can, yeah.
Okay, good. So we have two cases, either it's interior node or leaf node. If it is leaf node, then the cost is some constant of per primitive times the number of primitives inside this node. If it is an interior node, we have a constant cost of traversing to the child, and also have this sum of for all the child, we have this condition probability of traversing node from traversing to these children from our current node and the cost of our children. So that's where the recurrence relationship comes from, because we recursively call this cost function at here. So this looks like totally theoretical. What is it get useful? In the current form, the cost function is just not easy to calculate, but there is the surface area heuristic, where it expresses conditional probabilities as geometric probabilities. So in our case, we have this conditional probability of from our current node going to this particular child. We can use the surface area heuristics, which states that the ratio of the surface area of that child node to the surface area of the parent node is proportional to this probability of we want to go into this particular child. And then we can, after we have some substitution and simplifications, we get this cost function, which gets simplified by the surface area heuristic, where it does not have any recurrence relationship anymore. And however, surface area heuristic have several assumptions which make it not entirely accurate. So first, reagents are uniformly distributed outside the scene bounding box, which is definitely not true because usually we have a camera and all the rays shooting from the camera. Also, redirections are uniformly distributed, certainly not true. Rays are not occluded, certainly not true. So because the surface area heuristic is not very realistic, several fixes are proposed. And so if you want to learn more about this, you need to going to read the paper. The paper linked to several other fixes, but I will just use surface area heuristic because that's the general technique doesn't change. Then let's talk about BVH constructions. There are a lot of different ways to construct a BVH. They are top-down and bottom-up. If you read a parser before, that should sound really familiar, because BVH construction and parsing are kind of similar kind of job. They both kind of want to transform a sequence of primitives into a tree structure. So the technique used is kind of the same. And incremental construction by insertion just means that we have empty BVH and then we insert primitives one by one. And finally is the linear BVH approach, which I don't really understand that part of the paper, so unfortunately I will not talk about that. For top-down construction, we start from the root with all the objects, and then we recursively split the primitives into disjoint subsets. This is probably the most popular approach to construct a BVH, and if you all have implemented a BVH before, this is most likely technique that you already have implemented. So the pseudocode looked like this. This is a stackful version of pseudocode instead of using recursion, but the idea is the same. When using recursion, since we have a non-tail recursion, we need to put them into a stack. That's why when we do it in the loop way, we need a stack. And so first we push the root, and then we do a while loop to check if our stack is empty. If it's not empty, we pop the current node to process. And if the current node is a leaf, then we just use a leaf. Otherwise, we traverse to all the children's by push them into the no, sorry, not traverse, but we split the primitives into children and then put children into the stack. So this splitting primitives of node into children is kind of a customization point for the top-down construction, where a lot of different techniques can go on in here. We can split primitives by arbitrary criteria, but in practice, we usually just split them by axis-aligned planes because it's faster. We can either test all the axes and select the best one, or we can use some heuristics such as round robin, which just means the first time we select the x-axis, the second time we select y-axis, etc. And z and x. There are several ways to split based on planes. The first is spatial medium cut, which means cut the bounding box in the middle. This can be problematic if, let's say, most object is on the right and the left-hand side contain almost nothing. So we can have highly unbalanced tree if we construct it, if we split primitives this way. Object medium split, which we sort the same primitives along axis and split them into two halves. This is a pretty easy approach and is the one used in the reshading in one weekend we did before, if you still remember. And the third one is split based on the cost model, which tie back into our previous talk about cost functions. So the idea of this is to try to minimize the cost function locally to have high quality BVH. Since when we do BVH construction, we still don't know about the children yet. We cannot use the cost function of the children nodes. So what we need to do is to approximate the cost function by treating children as leaves. So in here we basically just go through all the children's and use the surface area heuristics to calculate to approximate the cost. But this approach can be a bit problematic because we can have large children and small children with bounding boxes of very different sizes. So there's a refinement of the previous approach by penalize the overlapping of child bounding box using additional term in the cost function. So we have this additional term in the cost function where we have a constant for penalty, and also it times the volume of all the bounding boxes of the children divided by the bounding box of the current node. So there are several algorithms to perform the splitting if we use the cost function. We can evaluate all the splitting planes, which is known as sweeping, but it can be costly. alternative approach is called binning, which is, we can divide the splitting extent into equally spaced bins, and then the cost function is evaluated only at the boundary of bins. So binning definitely cannot provide create a BVH as highly quality as sweeping because we don't perform that much calculation, but still the quality of binning is high enough that it's almost neglectable compared to sweeping, and it's massive speed up. There are also bottom-up construction. Bottom-up construction use an algorithm called agglomerative clustering, which is the idea that we initially have each primitive as a cluster, and then in each step we combine to close this primitive into one cluster, and then we just repeat this process until we only have one cluster, and that one cluster will be the root. This way it can have very lower global cost compared to the top-down construction. So, but it is very expensive to construct. Also, the top level may be poorly locally optimized, unlike the top-down approach, because we construct BVH bottom-up, and this can be a problem because we usually spend more time traversing the top levels of the tree instead of like the most bottom level. Then there is incremental construction, which is the oldest technique to construct a BVH. It starts as an empty BVH and insert primitive one by one. It is useful if we don't know full input upfront because we can just stream the input from internet or something and then just like insert them into the BVH. But on the other hand, it creates pretty low quality BVH. As I said before, we will not talk about linear BVH because I didn't totally understand that part of the paper. So after we construct a BVH, the next step is we need to perform some optimization for it because we can't evaluate the cost function of children during construction. So we use some kind of local approximation, but we can always build an initial BVH and then try to improve its quality. There are several ways to optimize BVH. The first is tree rotation, which is inspired by balancing binary search tree. So in binary search tree, we do this kind of balancing act to make the tree like just more balanced. And the same kind of technique can be performed on BVH. And we also can perform insertion-based optimization and subtree collapsing, which means we in the case in certain kind of BVH construction algorithms, for example, bottom up, we can have the situation where we have a BVH node with only one child, and in this case, we can just get rid of this node and then use this child as a primitive node. Now, let's talk about extensions for BVH. First kind of extension can be made is spatial splitting. So remember, bounding volume hierarchy is splitting objects, not space. but it can be a poor fit for scenes with overlapping primitives of non-uniform sizes. So in this case, we have two very long thin triangles, and our BVH just handle them very poorly to generate largely overlapping bounding boxes. On the other hand, spatial splitting like KD tree are great in those cases, and we can have some kind of same benefit if we relax the restriction of BVH where each primitive is only referred once. So if we can have multiple different nodes refer to the same primitive, then we can have a tighter bounding box. But on the other hand, both triangles in this case will be referred by both bounding boxes. No, sorry, both nodes. Also, the other technique widely used, especially nowadays, is wide BVH. So BVHs with higher branch factors are known as wide BVHs or multi-BVHs. They can utilize SIMD or SIMT units better because we can test one ray against multiple bounding boxes at the same time. They can be more memory efficient because there are few interior nodes than binary BVHs. But on the other hand, because we have a BVH node with more than 2 children, we will have the problem with empty slots where a node where most of its children is empty. So whether wide BVHs can be more memory efficient is highly dependent on the number of empty slots, and this is one area of research. There also a problem of dynamic geometry, where we have some kind of transformation of geometry that will invalidate pre-computed data structures such as BVH. There are two different approaches. First, we can reconstruct BVH from scratch. The second is we can refit AABBs in a bottom-up fashion, which is easy for AABBs since for AABBs, we can compute the bounding box of parent as a union of the children bounding boxes. It is hard for other bounding geometries such as bounding sphere. It is very fast, but it can lead to overestimation. So there's a heuristic to calculate the BVH degeneration, which is proportional to a ratio of parent surface area and sum of surface area of the children node, which again, the surface area heuristic. And if we use surface area heuristics, then we can see if the cost function get too high, then we know our BVH is degenerated enough, then we reconstruct the BVH from scratch, and otherwise we refit AABBs. Shouldn't have this. I don't know why this is here. But there are two-level hierarchies which is widely used in today's APIs, such as VOC and DX12 objects, because that's what drivers support those days. And they are good fit for most dynamic animation, where most dynamic animation come from rigid body transformations, which is definitely the case for most real-time applications. And the idea is to have detailed bottom level BVH per mesh, and we can generate them offline with its static geometry. And even for the top level, we have some kind of lower quality BVH, but then they need to be constructed fast. However, the quality of top-level BVH does impact efficiency, especially when there are large overlapping objects, which can reduce calling efficiency. So, in previous when we talk about spatial partition, we talk about those two really weird, long, thin triangles, which is uncommon. But for this kind of two-level hierarchies, this kind of large overlapping object can be a real concern. And we discussed that when we talk about ray tracing in Call of Duty, or what game? I can't remember when we discussed that. And in one of the previous weeks, and we talk about how this can be an issue.
I think it was the Call of Duty talk.
Yeah. And we have what's real-time ray tracing APIs usually have this kind of two-level hierarchies. So for DX12 for Vulkan, we have bottom level and top level. For objects, it's more flexible. We can have multiple levels. But hardware is really does really only support two levels. There are also hairs and furs, which are really poor fit for AABB for the exactly same reasons, because they are long and thin. So oriented bounding boxes can enclose such objects much tighter. And the two-level hierarchies can also help, because we can use OBB only for high and fur, and then for the top level we can still use ABB. There are also different ways to have more compact representation to save memory. We can reduce the precisions. There are various techniques to make this possible. Some of them use offsets from the parent node, for example, to make the floating point smaller, so we don't need that much precision, for example. We can use compression techniques. We can have parent plane sharing, because child nodes share at least 6 planes with the parent node. So there are some data redundancy in the bounding boxes of the parent node and child node. So that's something that can be used to have more compact representation. We can use triangle stripes, for example. We have implicit indexing. So if you remember a heap data structure, where in a heap data structure, we don't need any index address to the children, because the root is index 0 and its children is 1 and 2, and then its grandchildren is 3, 4, 5, 6, etc. And it's the same kind of idea that we can use for BVH to avoid storing the index of children. Now let's talk about the traversal. So the pseudocode for BVH traversal is like this. This pseudocode is also stack-based instead of using recursion, but the general idea is that at each node, if our array intersects with the bounding box of this node, and if this node is an interior point, then we just deal with all the children. Sorry, this should be push child instead of push node. And then otherwise we test whether array intersects with the primitive. There are different kind of traversals we want to perform. First is traversal, which is what we want to use most case and what BVH is optimized for. Also, any heat traversal, again, I want to mention that this paper's terminology is different from DX12 and Vulkan, where any heating here it means whether we hit anything or not. And this can be useful to calculate stuff like shadow or illuminations. And then there are multi-hit traversal where we can calculate all the intersections of ray with objects, or first n intersections. There are certain numerical issues regarding of traversals. There can be false misses and false hits. And false misses can occur if the distance between the entry and exit point is less than the 2 units of least precision. Based on this analysis, there are algorithms for more robust traversal to prevent numerical issues. String traversal means that we can trace multiple rays at once, and then we put the ray into a stream and do ray bounding box intersection altogether. This way, we can amortize the cost of accessing data and the traversing. On the other hand, if we have divergent rays, we need to split the stream into substreams. So this method, the efficiency of stream traversal heavily depends on how coherent our rays is. And if our rays are very coherent, then this way can utilize the SIMD and SIMD code very well. On the other hand, if our rays are mostly divergent, then the overhead makes this method not worthwhile. For the GPU traversal, the challenge is due to non-locality of data accessing and control flow, as we said before, for the divergent rays. And the control flow divergence can be mitigated by splitting the traversing loop into 2 separate loops, one over nodes and another over primitives. To prevent stalling when the GPU thread is down and just waiting for other thread, new rays are loaded from the global working queues into the persistent thread. So this idea is kind of like a thread pool in the CPU land, except we are doing data parallelism instead of task parallelism. But the idea is like this: we just fetch array, and then we just keep doing this traversal in a while loop. And if we find the intersection points, then we fetch a new ray. And this algorithm is called persistent speculative while that performs some other optimizations in the inner loop. as we said before, we have two different while loops, one for the interior nodes and other for the primitives. There are some other BVH applications beyond just ray tracing. If we want to do illumination or shadow computation, we can just use BVH. We can directly using volume rendering with BVH without even have some kind of primitives. And BVH can also be used for collision detection, but I don't think it's that popular. I think other acceleration data structures like KD tree and octa tree are still more popular in that space. Then the paper started to talk about several best practices for BVH if we want to implement one. For construction, the paper recommends using top-down construction with sweeping and using surface area heuristic-based cost function. And then we can use binning instead of sweeping to speed up. And then we can also improve the quality by using optimization algorithms such as tree rotation and insertion-based optimization. For interactive or real-time applications, the paper recommends to use two-level hierarchies, but also APIs already implement BVH using two-level hierarchies, so we don't even need to worry about them. For traversals, for incoherent rays, the paper recommends wide BVH with SIMD test one ray against multiple boxes instead of with streaming traversal where we have multiple rays to test against a single box if we have incoherent rays a lot. For GPU, the paper states that wide BVH can be too difficult to implement, so it's recommended to stick with binary BVH with per thread stack. Also, this robust traversal paper can be used to avoid numerical issues. So for CPU and GPU, both have its strengths. GPU is better for interactive or real-time applications because it's high throughput and it can just deal with a lot of stuff. But CPU GPU memory transfer can be a bottleneck, so it is recommended to just upload everything to the GPU once and then perform all the calculation on the GPU and never do perform CPU GPU memory transfer. CPU is better for large complex things where GPU's memory may not even be large enough. And CPU can also be parallelized by, for example, just have multiple machines. So that is what production renderings in films prefer. There are still a lot of open problems with BVHs. For example, constructing surface area heuristic optimal BVH is believed to be NP hard, which means we have no idea how to do that. And so we also have no idea how optimized our current BVH is. Also, and for the wide BVH, there are two choices. One is to construct them directly, and another way is to converting them from binary BVHs. And there's still no consensus on which approach will provide higher quality BVH. There are also problem of traversing from non-root node, so we can save some calculations. But on the other hand, we need to refer to some inner node of the BVH somehow. And then that's where we can traversing from that point. Also for non-polygon objects, like hair and furs, it receives less attention than just polygon objects. So they probably still have a lot of space can be improved. Yeah, that's the presentation. Any questions before I end the recording? Okay, I will end the recording now.